They usually come in over there, and they're coming in like a minute or two after.
Oh, no, that's what. We don't have to start on time. Okay, it says our stream health is good. All right, I just got the.
If you hear anything, thank you. Testing.
My apologies, actually. I didn't have time to charge all the microphones.
Since he gets official credit for this 1 hour course,
Oh, okay. No, that's fine.
he may want to.
No, I didn't.
So he may just do it automatically.
No, and I didn't ask him because he was in a meeting, but I just wanted to have. Yeah, and since you know what I look like, and you're on the committee.
Share the first name.
Yeah, there was a lot of similarities. I did a clustering analysis. It seemed natural.
Interesting.
Yeah.
You go by William or Bill?
Billy.
Billy, okay, good. So hopefully either reduce attendance is either because everybody's online or because it's the midterms and everybody's totally burned out. I don't know.
Yeah. Maybe a little bit of both. I know that the CDS, a lot of the CDS students, they come in like a couple minutes late because they're just they're just down the hall or whatever.
Well, we're in a hurry to start. We can wait till they come.
So we are live, just so you guys are aware. Just because we're having some weeks, so just watch what off-color jokes or whatnot.
Yeah. So
I will add any green jokes.
So you want me to wait a couple of minutes? Okay.
It sounds good. Yeah.
It sounds good. Cool.
I'll edit this part out. So I got.
Perfect. Perfect. Hey.
It still doubles our numbers.
Just a couple reminders. If you repeat the question, that's beneficial. If you stand too far that way, I can't see you after the camera. So it's good, like right in front of your computer is good. There we go.
And really, it's always good to just give a little bit of a dance in the beginning.
This is my dancing.
He was playing with the light. He was keeping the light just over his head.
Okay. I think Tim was good.
Who gave him a lot of money in exchange for that to happen?
He's like, projects and stuff. He's like, I can do that on like 1-3.
They would have been convinced me. It's about time.
Yeah. Maybe some benefits. People can play around. We would play around on this. We say Neo for they graph that.
Here's a structure that kind of falls away.
It's a new house. Social network. Yeah.
Is Gideon coming?
Do you ask him?
Yeah, a couple minutes. Okay.
Do you?
I'll report. Yeah, probably. Okay, why don't we get started?
Sure.
Have Billy here today and tell us about spies and other interesting things.
Spies and pills and storks. Yes. Hello, everyone. My name is Billy, and today I'll be talking about classifying pill spies using storks. And so an outline of what I'll be talking about is I'll do a quick introduction to shape analysis and a specific measure called circularity, which is the measure of how circular something is. And then I'll get into the SPY part, which will be the bulk of the talk, maybe about 40 minutes. And then the last 5 minutes or so, I'll be talking about the application of SPIEs to some NIH pill data. And then I'll also be talking about a cross-validation technique that will be applied specifically to that data set. So a quick introduction to shape analysis in one slide is shape analysis describes shapes. Some find singular values that describe a shape using just a singular statistic. Others try to build very complex models, maybe a rule-based system or some other technique. So to start off, I want to ask the question, how would you describe this shape? Anyone?
Dinosaur.
Okay, just dinosaur. Okay. T-Rex, okay. Do you have like a measure to describe how dinosaur that shape is? No? And then how would you go about trying to describe a dinosaur shape?
I'd be able to do some three-dimensional schemas.
Okay, maybe some three-dimensional analysis. Two-dimensional, yeah. Okay.
It has a tail.
Okay. Does the tail have to be in a certain location?
It has to be the furthest point from the nose.
From the nose, okay. So you're gonna look maybe at like the farthest distance between pixels on an image, and if it's really large, that means it's a dinosaur.
Good, because I was wondering how you're going to identify the nose.
It's curled up like a dog.
Yeah.
His tail's nice.
Okay.
What if I take off my optical regime hat and I put on my Fourier hat and I say, it's actually, the main feature is that it's a binary image. It's black and white. There's nothing else in there.
Right. So you could go into Fourier space and try to find some combination to describe this shape and find that signal in the Fourier space. Yes, that's a very common first approach, rather. And so, absolutely. So, welcome to image analysis. It's hard to describe shapes in an intuitive manner. And so, let's go over one of the more palpable ways of understanding shapes. And that is how circular something is, a measure called circularity. So when the shape is a circle, the statistic of circularity will have a value of 1. And that's because the circularity is just the parameter squared divided by 4 pi times the area. And so if you plug in the perimeter and area equations for a circle, it turns out to be 1. This statistic of circularity has the unique property that when you're looking at regular polygons, it also has unique values. So this is a great statistic to use for discriminating circles and regular polygons because you have that unique value, and when you analyze an unknown shape, you just find the value that it's closest to and categorize it to that class, right? There is it's a simple intuitive statistic that's very helpful to start off with. The problem,
Going back to it,
yes.
I would have thought, putting on kind of like, from a complexity point of view, or putting on a fractal hat. I mean, wouldn't I think about things like, T and A being parameterized by the length of my ruler? And I'm thinking, so this is like, what is the circumference of the island? And the answer is the island depends on what ruler I'm using. This is what Mandelbrot taught us, right? With a very small ruler, the perimeter approaches infinity in length, right? So do I have to worry about that kind of stuff or not?
I have not encountered those kinds of issues because we're typically using discrete images who are usually pixel-based images. Yes, pixel-based images.
So it's also only getting the shape relative to a circle, not the shape relative to the body of the image, the outline of the image, the boundaries of the image. So it's not a small circle and one that fills it are going to show the same.
So I'm a little confused about your question. Are you trying to say that this is...
Dinosaur picture.
Okay.
Hey, Billy, real quick, can you move your mic down just a little bit to that?
So that dinosaur practically fills the space.
Yes.
So if I had a small circle that was a 1/10 of the area, would it show any different than one that was 3/4 of the area?
Okay, so the question is, does the resolution of the image change your value? And Is that your question?
Yeah.
Yeah. Okay. So yes, it does, and
Your statistic?
well, no, this on circularity.
On
Or in circularity, we'll get to.
how is it affected by?
So I mean, it won't always consistently give the same value. So for example, if this dinosaur is rotated, you will have different pixels. Try to how do I simply say this?
You break your equation again? It was just area, relative areas.
Right. So you
Perimeter.
perimeter.
Still, perimeter
So
doesn't have orientation.
so if you have less pixels, you have less finite measurement on that image. So you get a more like. So if you made this only like, I don't know, let's just say for the sake of argument, 20 pixels by 20 pixels, you will have less pixels to make the minute details of this claw.
Right.
And so you would basically maybe have 1 pixel just be 2 blocks for the claws instead of 20 pixels for each claw, right? So that will change your statistical circularity, absolutely.
Okay. But it doesn't. If it was a perfect circle, the only change is going to be the pixelization.
Well, okay, so if you have the problem of, let's say, a 9 by 9 square as your image, how do you make a circle in a 9 by 9 square? Do you make it more star-like, or do you just fill in the center? So, for example,
Yeah.
here's my image. Here's my 9 by 9 square.
Right.
So do you make the circle be this? That doesn't look like a circle, that looks like a T, right? Or do you just fill in the center? So these questions in the lower resolution really matter, for especially when you're trying to measure things with simple statistics like circularity. Does that make sense?
It does, but if I've made my circle be the center square of your 3 by 3,
Right.
and my alternative circle be all 9,
Mm-hmm.
it has the same shape,
Mm-hmm.
but it scales at a different size.
Right. No. So in that case, it does end up being the same, but the algorithm how you create a circle really matters. So there are some algorithms that make circles that more similar to this, and so that all the point I'm trying to make is like your algorithm and the dimensionality really affect your values for circularity. Okay. One of the issues for circularity is that it doesn't help you describe the shape in reality. So, for example, if you have circularity equal to 1, how many pixels does that correspond to in a given image? If I'm looking at a square and there's 50 white pixels making up that square, out of 100 pixels total, is that even reasonable? Circularity doesn't tell us answer those questions. And so circularity is limited in its inference capabilities. And so the goal is to come up with some measure that's intuitive, that gives us an exact unique value for those, for different shapes, but also a metric that allows us to make inferences in the real world. And so shape proportions and encircled image histograms attempts to do just that. The shape proportions describe shape as a proportion, the proportion of white pixels. And then we utilize the binomial distribution to make inferences on how that shape will exist in reality. And the encircled image histogram is the realization of the proportions. And so its acronym is SPEI, because it's SPEI and makes it easy to remember. So just a quick formalization. I tried very hard not to include lots of text to over-encumber us on a Friday afternoon, but these are important to understand what we're doing moving forward. And so let's just go through these and let me know if you have any questions or if you're confused by anything. So AN is just the area of an n-sided regular polygon encompassed by a circle.
Is it the area of the polygon or the circle?
Area of the polygon encompassed by a circle. So I will go over an example in the next slide, in the next couple slides of that. Then AC is the area of the circle bounded by a square whose radius equals half of the square's side. And again, we'll see an actual example in the next slide. AR is the minimum bounding square, which envelopes a circle whose diameter equals that square's side. And then R is the radius of the circle corresponding to AC. PC is just the ratio of AC over AR, and PN is the ratio of AN over AR. Enough symbols, let's look at a picture. So this is your circle. This is your minimum bounding square. And so in this case, you have that your PC, the area of the circle, divided by the area of the square, would be the number of white pixels over the total number of pixels. So the black square is covered, right, by some of these white pixels. So it's the total number of pixels that make up this image is the denominator, and the numerator is the total number of white pixels. So that's what it looks like for a circle. Now, for a regular-sided polygon, let's look at a pentagon. Here, we envelop the polygon in a circle, and then find the square that envelops that circle. So notice, so this line is just a reference line. It's not actually in the image what we're calculating. But you get the point that, for example, these bottom corners are not all the way at the top. It's not the minimized enveloping square. I am finding the smallest circle that envelops the polygon, and then the smallest square that envelops that circle. Subtlety that's important. And here's another example without a reference circle. This is why finding the circle is important, though. So for example, if this square was rotated by 45 degrees, and I just found the minimum bounding square, I would just have an image of white pixels. Here, though, if it's rotated by 45 degrees, it's this image. See? So for example, here with the reference line, imagine just rotating this with any degree. I'm still going to get this square. Yes? Right. But, for example, this image will look different. The composition will look very different if this is rotated by 45 degrees, right? Yeah, without the reference circle. And so, because we've constructed our images in such a way, we can have for any regular polygon unique values, and for a circle. And here are just 10 of those values. This, as you increase the number of sides, this will converge to pi over 4, which is the unique value for the circle. So, we have a metric with unique values. Can we make inferences using this metric? So again, to really emphasize this point, SP, the shape proportions, are the proportion of white pixels, and it's surrounded by our uniquely bounding square. That is the statistic summarized in a slide. And so the goal is, okay, how can we understand how this image exists in reality while looking at a digital image? Traditionally, one of the first steps to an image analysis is look at the pixel counts for your given image, and generally try to look at the shape and say, oh, this pixel count shape keeps on reoccurring. Maybe that is its own class. That is called image histograms, and it's just simply the pixel counts. What we'll be also looking at are encircled image histograms, which is the pixel counts after the shape is encompassed by a circle. And we'll go over some realizations of this in a couple slides. So, this is just a given image for a shape, and we have the black pixel counts on the right here, and the white pixel counts right beside it. And so you just take this image and count all the black pixels and all the white pixels, and you get your counts. It's that simple. After you get rid of the black pixels that are not needed, and you envelop this shape in a circle, what happens is that you reduce the number of black pixels, right? And so your white pixel count stays the same, and the black dramatically decreases. So again, just by comparison, to make sure it's very clear, you're removing a lot of the black pixels that are not needed for your understanding of the problem. Now, you might have a case where you just have a square of white pixels, right? In that case, you're going to be adding black pixels. But basically, you are adjusting the black pixels so that you're on a level playing field for your analysis. Okay. So the realization that we're going to try, or the realization of shape proportions into reality is we're going to be utilizing the binomial distribution. And in case anyone hasn't used the binomial distribution in a while, here it is again. In this case, we're going to have our x be the number of white pixels, which is formally the number of successes that we're going to have. Zeta is going to be the resolution or the total pixel count in an image, and that's going to be the number of trials. N is the shape proportion for our given shape, and that will be the probability of success. So after you simulate for a large number of n, you get this pattern, this fan-like pattern, where you basically each shape falls along a line. And you also have here the dotted lines being the 99% credible intervals associated with each shape. And so here you can see that they basically follow this very distinct line for shapes. Yes? Oh, sorry, good question. So the shapes are n equals 3, so a triangle, n equals 4, a square, and then you go down to n equals 8, an octagon. All regular. So they follow a nice, unique pattern. Okay? So we looked at an example of some simulated data, but let's actually apply this to some actual data. So here we're going to apply it to shapes, regular polygons, from triangles to octagons, side length equal 1 to 125. And so here are 4 examples where you have the side length equal 1, and then the side length equal 125. And again, another example. Additional edits were made just for presentation purposes, so these gray pixels were actually black pixels. Okay? And so, turns out, when we apply the encircled image histogram to our data, we observe this same pattern where you have these lines. And one of the unique characteristics is, and so you also have the 99% credible intervals as well, and they follow, they're pretty close to this actual dotted line. And so we basically have found a method that works well, that falls in line with the theory fairly well. Any questions up to this point? So, we talked a lot about theory and some fancy math, but you can look at shapes and say that's a square, that's an octagon, but who cares? So, the next step here is to hopefully apply this to some NIH pill data to try and classify the pill shapes correctly based on their shape. So, this pill database has 15 different classes. Some of them are here. And so you have like the capsules of approximately 1,000 observations, while you have the semicircles, which have as little as 2. And so again, the goal is to correctly classify the pills by their shape. And so you might ask, why not just try and classify the pill correctly? Like, oh, if I just take a picture of that pill, that's Tylenol. Someone has tried to do that. Didn't work out so great. And so now the community has said, okay, let's try to classify these pills like just by shape and just by color and just by text, et cetera, et cetera. And so what we're trying to do is classify just the shape.
Was the unsuccessful approach or machine learning approach, or what?
So the current approach that the inspiration for this application, there has been an approach that uses a rule-based method and a neural net, and if I remember correctly, the rule-based method was won out. So the issue there is that it's a very complex model and it's not very intuitive or understandable. And so our hope is that we have a very simple model that does very well and is easily interpretable by a large technical experience for a given audience.
Just out of curiosity, and just as kind of a background of you, when pills are made like this,
Mm-hmm.
does Lilly create, for example, new capsules for every pill, or are there such things as like standard capsules? So almost maybe I need to put a certain amount of medicine in the capsule.
Yeah.
But can I just use a standard capsule, or the capsule is always created novelly for each medicine?
Right. So the question was, are capsules or pill shapes standardized in some fashion? And I do not know if they're standardized in any way. However, I do know that pills are attempted to be identified by giving a unique classifier, and sometimes it's easily identifiable on the pill, sometimes it's not, depending on how it's regulated. And so, I mean, one of the problems is so if you were at a crime scene, obviously, there would probably be some desire to confuse the pill with another one. And so they might mix up the text on it or something. And so going just by the text wouldn't necessarily always guarantee that you have a good match. And so there's lots of different complications given the different unique problems that you might encounter.
So just real quick, I think to follow up, it does, I mean, so this, I have not seen this technique that you're using, but the idea of using sort of traditional convolutional neural networks to support, taking large data sets of images and then extracting features and then being able to say with some probability that it's a type of pill, and it can be more specific, like this is Tylenol from 1981. Usually, I mean, as far as I've seen, is sort of a technique that people are using to be able to classify image data. So are you saying that that approach was maybe tried and not worked, or this was sort of an alternate technique that was applied, and it's sort of like let's see if this the approach is going to be better than traditional convolutional neural networks.
So would you say that your question is does neural network has the rule-based method been more successful than the neural network method? Is that your question?
Yeah, or is this method that you're talking about here?
The SPY method? Okay, so the next step in my dissertation process is to apply the SPY method to this data set. I have not gotten to the point of applying it to the pill data. That is, it's on the docket. But the last year at an IEEE conference, they presented one of the papers was on whether using neural net or a rule-based system was more effective for classifying the pills. And so in their paper, they described a rule-based system much more effective.
It gives a calibration, what about, so you say much more effective, we're talking about like, yeah, we have like 99.9% ability to resolve these things, or is like 50%?
So
Like one type 2 errors?
So they were able, I don't have the exact value memorized, but it's ballpark to be around like 90%. And so most of the issues, though, are with these lower numbered classes. So like semicircles, hexagons, pentagons. Turns out classifying pentagons and polygons with greater than 5 sides is very difficult. And so that was one of the areas that paper specifically struggled in. And so moving forward, the next step would definitely be also ensuring that the approach that I described really does well on those lower numbered observations.
The lower number of observations are so close as being identified as a circle by a rule-based method. Is that what you remember?
So restate the question, please, because I don't.
Is the problem with identifying the lower number side objects, is it because to a rule-based system, these can be easily confused with a circle?
So the issue, so maybe if we look here, just looking at this image of the encircled image histograms, you can see that when you have like lower resolution, which is going to be more centered down here, maybe images only composed of 9 pixels or something to that effect, right? You're going to have lots of overlap.
Yeah, and even
And
if you move further out, your slopes are getting closer and closer together, so n equal 9, 10, 11.
Right, exactly. So basically, one of the problems is that when you have increase the number of sides, it becomes increasingly, you need more and more resolution to make that distinction between the sides. And so you need to if you want higher and higher classification rates for more and more similar looking polygons or polygons with greater number of sides, you need more resolution to make those classifications. Okay. So going back, there's a lot of good questions on the previous slide about the number of class counts. One of the issues generally when training a model is that you don't have enough data to train the model, right? You don't have enough to make a model to make predictions for your given class. So for example, in this case, we only have 2 observations for the semicircle class. I mean, how would you consider building a model on 2 observations using any kind of machine learning, artificial intelligence, classical statistical learning techniques? And so, remember, one of the first modeled validation techniques that we have is cross-validation, right? And specifically what I'll be talking about or referencing in this for the next couple of minutes is k-folds cross-validation, right? Where you split up your data into k-folds, build a model on each fold, and for those given folds, you confirm that you're getting the same results from each of those observations from some of those folds, right? There's a more sophisticated technique where you split up the folds by preserving the proportions in your original data, and so you call that stratified k-folds cross-validation, right? So for example, if your data had 2 classes of men and women, and they were both equally represented in your data, then in each of your folds, you would want approximately half men and half women in each of those K folds. What if, however, you had data where it was 90% men and 10% women, and you had, let's say, let's say you had 100 observations, and you had 97 men and 3 women. And so then the goal is, okay, let's say I want to do K equals 10 cross-validation, and I want to do it stratified. Well, in that case, you would need 0.03 women represented in each of your K folds. But when you do K equals 10, you have 10 observations in each fold. It is impossible to achieve 0.03 women in each of your 10 observations, right? Because the lowest number of women that you could have is 0, and the highest is 0.1. So you cannot do stratified cross-validation in that scenario. So what is the solution? One of the solutions that I propose is trying to just overrepresent the smaller strata. So you have at least one woman in each of your K folds. And that ensures that each time your model is at least seeing a woman observation before it tries to make any predictions about that subclass. And so in this approach, basically we see that when you have very drastically different strata, traditional K-folds cross-validation is very erratic and unstable across different noise levels. So if you have very unnoisy data, it's fairly similar. But when you increase the noise in your data, it drastically increases the instability of your models and your predictions. And so while stratified overrepresents K-folds cross-validation, which overrepresents the smaller subpopulation, is more stable as the noise increases. And so the next step is basically to apply when we do the modeling technique to use stork, because we have such disparities in the counts for our classes. Any questions?
Can you go back to your classes again?
Yes.
You have 15, something doesn't look right. Total 2,800 fills.
Yes.
15 classes.
Yes.
And then you have counts of some of those classes.
Yes.
Okay. It looks like there's close to 1,000.
Right.
Missing.
Right. No, that's true. So if I listed every single class, I would have an entire slide just dedicated to that.
But
Yeah.
They're all far less than 39. Those are the top 5 and the bottom 1.
So capsules and round pixels, or capsules and round pills, make up the majority of that figure.
Not by that show.
No, excuse me. Capsules and ovals.
Ovals.
Sorry. An oval is close to a circle. The point of only including some of these classes was just to make the point that you have these big disparities between the classes, the counts of the classes. And so using just out-of-the-box K-folds cross-validation, you would have these instabilities when you were trying to build your model. And so the 3 things that I discussed today, the SPEI is primarily focused on images. The pill data is the application, but the stork part is not only applicable to image data, but any kind of data where you have these large disparities, whether it's polling data, economic data, etc. So it's much more generalizable. Yes.
We got a question from online. It says, why is the training necessary? We know what a triangle, square, and circle look like. Why not measure that against the image?
So repeat the question, please.
Why is the training necessary? We know what a triangle, square, and circle look like. Why not measure that against the image?
I don't quite understand the second half of that question, but we train data because we want to build a model, and then we use other data that we haven't built the model with to confirm that we're getting similar results, so that we know that our model is stable and making predictions.
The question is this: since when you run a machine learning model and test data, and then you compare it to another piece of the data, so that you can figure out how good the predictions are, and you're assuming that one of them is ground truth. Okay. But the question here is, we already know what ground truth is. We already know everything about a triangle, right? It's a triangle. So why do we need to train anything? Why do we need to train the model and compare it to our ground truth? It's a misunderstanding of what you're doing.
Yeah, it's a triangle in context.
It's a misunderstanding of what you're doing.
Okay.
I think you need to summarize the discussion because that would not have been caught.
Yeah, so basically there was a misunderstanding about, from my understanding, what everyone has been saying is that there's a misunderstanding of what has been discussed, and basically that we're not training on the object, we're training a model. Right, does that summarize the conversation? Yes, okay. Okay.
So, Billy, just also, so in your paper here that you I guess you're presented it now?
At JSM, yeah.
So did you, in the paper you primarily laid out the formalism that you showed us here? Because there are no results in the paper yet?
So this paper is just for Stork.
Yeah.
And this lays out the formalization and some simulated data and some real world data, just comparing the results. The results, or the things I discussed regarding SPY, those results have just been submitted for publication last week. So this is hot off the press, if you will. But if anyone wants to see that working paper, talk to me afterwards.
So one question I have is that, so you basically have been showing us 2D images, essentially.
Yes.
But we know there are tools available. I was in the lab last week where they were showing us that you can just plop an object in and you can do 3D imaging of the object.
Right.
Does this methodology have a chance to scale up then to work with higher dimensional images?
I hope so. I have not, basically, my training is in mathematics, so I start out with the simplest case of a 2D image and work in complexity up from there. So I hope to try to expand this to more three-dimensional images and just greater number of intensities. So instead of just binary images, but do 8-bit images, which has 256 different grayscale counts. So yes, I hope to increase the complexity, but for right now, I'm just primarily looking at images in a 2D space.
Might be, for 3D design, would you consider random projections of it in two-dimensional space and see if those have statistical properties? So that might be the way to generalize it.
Mm-hmm.
Shadows of a real film.
Yeah.
Never solved the dinosaur.
That
Does a dinosaur have, would a dinosaur's image, 2D image, binary image, have a slope, like a square and a triangle that is unique?
So one of the problems with dinosaurs is that they have different. It's actually it's very hard. The next step is obviously to say, okay, what about non-polygonal shapes, right? And so the next thing would be things that look close to like polygons, right? So for example, a real world example that I could think of is it is the general assumption and is wisdom that we can discriminate tumors, right? We can discriminate tumors whether they're malignant or benign, and by looking at them. So there has to be some kind of shape that says, okay, this is malignant and this is benign. And then we do invasive testing, right, to double check those results.
Well, I'm going to just put a caveat on that. So I was just at a National Academy conference where the results from new high-performance imaging techniques show that at any instant in time, we all have like 10,000 tumors in our body.
Right. Right. No, so I guess this was a quick summary and kind of like just trying to get the main point across. So for like example, for mammograms, the prevailing technology used in practice is just taking an X-ray of the tissue, and that has a prevailing negative connotation of being inaccurate, right? Because it has a lot of misclassifications for basically saying that you have cancer when you actually don't. And so practically, the patients, while the mammogram itself is free in most scenarios, the invasive, biopsy is not. And so that is the prevailing issue for a lot of patients who have to deal with that. And so the goal there is to say that, can we just look at the mammogram and correctly classify it as is, because that is what is used in most practice. So yes, there are more advanced techniques that I have seen and read about, but those are not at the industrial level. Yeah, exactly. And so tumors are at least somewhat polygonal. Maybe they're more close to an oval or circle, etc., right? But the idea is, okay, can we apply this method of using SPEIs to correctly identify what a malignant tumor's proportion is versus a non-malignant tumor's proportion is. That's the next step. Dinosaurs, cats, birds, that's after. that's down the line where because you have the issue, like for a cat versus a dog, right? You really need a lot of resolution to make the distinct classifications for those, right? So when you have you have less pixels, they all have 4 legs and a tail and some ears. Like that gives a general similar shape, right? For cats and dogs. So for example, for cats, they have a more pushed in nose, while dogs have a more elongated, typically, unless you're looking at a pug or something, right? So you add complications here, but the canine has a more wolf-like shape, right? And so you get into those kinds of issues where you need more pixels to classify. Like you need a lot more pixels around the muzzle, the face, rather than having less pixels to catch those unique details. Yes. Yeah. Yes. P is the shape proportion. So
That's what I'm trying to kind of figure out.
yes. Any other questions, comments?
Tell us a little bit more about performance measures in the sense that, okay, in the case of the pills, it's kind of categorical, right? You get the right pill, you're going to identify the pill or it can't. But you have to imagine other contexts being not so much categorical as it would be as well. Maybe that a performance measure would be something like, is my technique for identifying the shape, is it robust if there's a noise beat or something? So robustness to noise may be more important than simply trying to get the exact color or something. So do you have any sense of I guess maybe it's too early to say, but is this technique, for example, more or less robust when it comes to having noisy image, for example, than it would be a neural network type?
Yes. Okay, so your question is this approach more resilient to noise in a given image?
Image degradation.
Yes. And so image degradation specifically, so like the aspect of like maybe some pixels being turned off or something. So the next step, which I have not formally gone through, is to try and understand, okay, how resilient is this analysis so that when certain pixels are turned off. So for example, let's just say, for the sake of simplicity, here's my given image, but in the middle of this shape, there's a giant black hole. And those are turned off because the sensor's broken or something, right? Then what will happen to the results? Well, intuitively, you can say, okay, you're missing a lot of white pixels there. So you're gonna, when you look at the plot, instead of being here, it'll be over here. Or actually more up here because you have more black pixels as well. And so for this, so for in general, what can you do when you have noisy images where some pixels are turned off incorrectly? If you make the assumption that the image the shape is completely filled, that there are no holes in it, you can fill in all your images and assume that it's not a cheese, it's not like a Swiss cheese, it's a cheese wheel, if you will. And so that will counteract some of your noise issues. However, it is sensitive to edges. So if your pixels are turned off at the edges, that's important because this will look more like a circle than 1, 2, 3, 4, 5, 6, 7, 8, 9, a 9-sided polygon. And so the approach that I have started investigating would be better when we know that the edges are not degraded. But we can calculate, for a given resolution size, we can calculate a probability that those how much those edges might have been affected and how off we might have been. So we might be able to calculate, okay, if the edges are in fact degraded, it could also be this possibly, but etc. So you can make probabilistic guesses as well off of that, but that's down the line. So if you know that the edges are preserved, but the inside is not, you can still get I presume, a fairly good estimation of your shape, but it depends on how many holes you have in your slice of cheese.
So along those lines, the Swiss cheese example versus the cheese wheel, if you were to, is there like a summary measure, is there a summary measure to tell the difference between an image that has a lot of holes in it for robustness and then an image that has one hole in it is equal in area to a small number? Do you look at entropy or something? Does entropy show you that?
So at least my intuition is to go and say, okay, what's the difference between the amount of white pixels I filled versus the, so basically how many pixels did I fill? And that's going to be divided by the total number of pixels in the image. And that's going to say, okay, I did a lot of fixing up here. So if that ratio is high, that says, okay, I did a lot of changes to the image. And that's going to say, okay, there's less certainty about what is exactly going on here. But if that ratio is low, like, oh, maybe only 1 or 2 pixels were turned off, then it's probably fine. So, but that's, again, I haven't done the formalization for that, but that's the soon to be coming. Yes?
Your description of pixel being turned off is implying that you can tell the difference between a pixel that's working and a binary output and one that's not working. But your description of it is it goes to the other color. You're just assuming it's a continuous shape. You don't expect to have any islands or holes or anything like that.
Right. So the question was, I am assuming that the shape is completely filled. It's continuous. There are no intentional holes to be there. And yes, so you have to make that strong assumption that your shapes are completely filled. It's not like like you're looking at, like if you had two circles, right? And you had one image was Swiss cheese wheel, there are going to be no holes that you can see through the shape of that circle. But if you're looking at a slice of that wheel, there's going to be holes in it, right? And so those are two different images. Even though they're both circular in their perimeter, if making the assumption of there are no holes drastically changes what you're actually looking at, right?
Where it was going is, if you have random placement of bad data,
Yes.
that's going to affect both the black and the white proportional to the relative variance.
Okay, so if one of the things I didn't explicitly clear was assuming that this is your image, assuming like this is your isolated largest white object, and I have isolated that. So if you're looking at galaxies, for example, right, you might have tons of little white pixels all across this image, and so I have ignored that for the explanation purposes. But basically, in your analysis, you have to be clear what you're looking at. Are you looking at the biggest white object, or are you looking at, like, you make the assumption, okay, the given image doesn't need any alterations. That is the shape, right? So those initial assumptions that you make are very important for what your results will be. And so in this case, it's easier and more palpable to understand because it's just a polygon. I'm assuming it's a polygon, and I know that there should not be miscellaneous strings or crayon writings or whatever. It's just that shape.
Elias is a nonagon, nine-sided shape.
Yeah, nonagon, yes.
We just mentioned one example where I think that it would be a good payout to keep in mind in a robustness issue, because I am familiar with an example where we're competing ways to identify objects, and the particles to train may take years to train. And following this iteration, there was a red team. So the blue team trained on the red team for years and years. And the red team met with some financial hardship. And so their soldiers ended up mounting a charcoal grill on their objects. And then all of a sudden we have now many years of trained U.S. devices that can't identify the object because there's this charcoal grill sitting on the opponent's device. And so used very high temperature, basically zero. And so there's only a tiny little section. I think that there are cases where maybe the robustness to the noise is even more important. I'm happy to take a degradation in performance if I can just be robust to
Yeah.
That's the thing about Bosnia, they only was shooting like 90% missile strike rate, and then afterwards they said, no, you don't. And it's because they're putting microwaves out in the field. They just opened the door and run. They're sending up a radar signature that said this is. They thought it was, just like a Russian great anti-air. So they thought that is that's right. And then when they went on the ground and we were doing the research, like, oh, okay,
Yeah, no, those are definitely worth investigating and keeping in mind for future research. Absolutely.
Okay, well, if there are no more questions, thanks for Billy for